All right, this lesson is on applications of integration, force and work. But before we start, I want to at least remind you how you calculate pressure at any depth h. So that's this formula here at the top of the page. Pressure at depth h is weight density of the fluid times the depth. And I actually want you to think about this common misconception. Imagine that these are three different tanks that are filled with water, completely filled with water, and they're all 10 feet tall. Obviously, I can look at all three of those and tell the volume is not the same. If you look at the formula, the only two things pressure is dependent upon are weight density of the fluid and the depth. So it doesn't matter what the volume is, which means the pressure at the bottom of each of these tanks would be the same. All right, now again, this lesson is really more on force and work, so let's look at those two formulas. We're trying to calculate the force on the side of a tank. We know the force on the side of the tank is going to equal the weight density of the fluid times the depth times the area. Work, when we talk about work, we're going to talk about trying to remove liquid out of a tank. Work is equal to weight density times distance times volume. Now, I think a key thing to do is learn the formulas in terms of what the variables represent, rather than, like right here, saying force is WH times area and work is WH times volume, because in many times when people do that, they get the H's confused in the sense of they think this is the same H. And if you look down here at the bottom, just to remind you, this H right here is a depth, so how far below the surface of the liquid something is. And this H in the work formula is a distance. Distance is something has to be moved to be removed from the tank. Let's actually look at our first problem. So we have this rectangular tank that's 8 meters deep, filled with water to a depth of 6 meters. It's shown on the left. And what we're trying to find is the total force exerted by the water on the end of the tank. So we're trying to find the force on this end of the tank. And if you note then, what we have drawn on the right is that end of the tank. Now, let's start by just writing down the formula. We know force is weight density times depth times area, which means when I look over here at this end of the tank, I've got to, one, be able to draw a rectangle that I can find an area of. So I'm going to pick a point. The name of that point is going to be 10, y. Here's my rectangle. That if I were trying to describe the area of it, I need to know this distance, which is 10. And this distance, which is some arbitrary change in y. I also need to know the depth. And the depth is how far below the surface of the liquid this rectangle is, which means I'm going to need to name this point, which is 10.6. And so h is our distance here, which, again, remember, anytime we're trying to find the distance between 2 points on a vertical line, we do top y value minus the bottom y value. So now, I think I'm ready to substitute. Now, the weight density of water is 9,800. That will always be given. You're not going to have to learn weight densities of different liquids. So the weight density is 9,800. The depth, h, we've just labeled as 6 minus y. And the area of that rectangle is 10 dy. So if I do just a little simplifying, not much, if I just multiply here the 9,800 times the 10, we're going to get 980,000 times 6 minus y dy, which is the force exerted by the water, that one rectangular region. Okay, but what we want is total force, which means we need to add up infinitely many forces just like that. So we're going to integrate the 980,000 times 6 minus y dy from, well, we have to find limits of integration. And on this particular problem, since we have a dy, we know we look at the y-axis for limits of integration. Now, people are going to guess here that it's either 0 to 6 or 0 to 8, but there's no reason to guess. First, think about the fact that water, talking about the force exerted by the water on the end of the tank, where is the water along the y-axis? Well, that would be from 0 to 6. All right, if you enter that on your calculator, you're going to get 17,640,000, and force is measured in newtons, which we'll just call N. Now, there's another thing you can do to check to make sure you have limits of integration right. So let me at least say this. If you want to check, another way to check limits of integration is to look at your depth and use your limits of integration. It should be that when I plug these two limits of integration in for depth, I'm going to get the minimum depth and the maximum depth. So let's talk about where we get a minimum from. If that rectangular region were right here, then the depth is 0. Let's see where I shaded. If it's right there, the depth is 0. You get 0 when you plug 6 into the depth, 6 minus y. The maximum depth, so the minimum depth was 0. And we got that when we plugged 6 into the 6 minus y. But the maximum depth is when the rectangular region is here at the bottom, and that would be a depth of 6. Well, we get 6 for a depth when we plug 0 into the depth, 6 minus y. All right, so let's look at a work problem. So again, I'm going to start with our work formula, which is weight density times distance times volume. And we're going to look at what we need to label in this diagram. So again, I'm going to start with just that arbitrary point, 10, y. I'm going to draw what looks like a rectangle. But on this particular problem, you got to think about the fact that this thing is going to have a volume, which means it's going to come out 15 meters. For the most part, let me draw that over here for you so you can see that. So if I labeled this distance here as 10, and this distance is a change in y, then on this box over here, this is 10, this is 15 based on this dimension, and this other dimension right here is my dy. So when I talk about volume, I'm talking about the volume of that box there. Volume of water that could be held in that box. All right, now we've got to also label h. H is a distance that this has to be moved to be out of the tank. So I'm going to need the name of this point, which is 10, 8. And our distance h then is top y value minus bottom y value. Here is going to be 8 minus y. So if I substitute what I know, I have a weight density of 9,800. I have a distance of 8 minus y, and I have a volume of this box right here, or the volume of water in that box, which is 10 times 15 times dy. And if you do a little bit of simplifying there, you should end up with 1,470,000 times 8 minus y dy. So if I multiply 9,800 times 10 times 15, I'm going to get the 1,470,000. But again, I'm not just looking for how much work it takes to remove that one bit of water out of the tank. We want to empty the tank, so we need to integrate to add up infinitely many So I'm integrating 1,470,000 times 8 minus y dy. And again, since I have dy as a limit of integration, I mean, if I have a dy here, I know my limits of integration have to be on the y-axis. So if I go back to this picture right here, this one, and I look, and I'm trying to decide what the limits of integration are, I might kind of struggle with, is it the limits of integration 0 to 6 or 0 to 8? And again, I'm going to remind you, you're removing water. Where is the water? On the y-axis, and that's from 0 to 6. If you enter that on your calculator, just evaluate the interval, you're going to get 44,100,000 joules. Work is measured in joules. We'll just use J. Again, a check on this to make sure you have the right limits of integration would be a maximum and minimum distance that you have to move things, meaning when you plug these limits of integration into that distance right there, you should be able to get the max distance and the min distance that something would have to be moved. So I'm going to show you here if let me get a different color. If we're talking about removing something from the bottom, we're going to move it out of the tank. It has to move a distance of 8. I get 8 when I plug 0 in to this distance, 8 minus y. If it's right here, I only have to move it 2 units to get it out of the tank. I get 2 when I plug the 6 into 8 minus y. All right, we're going to look at 2 other problems, but here's the thing I want you to think about. Anytime we're emptying either all the water out of the tank or part of the water out of the tank, for this particular problem, it's always going to go back to an integral that looks like this. The only difference is going to be the limits of integration. So on this problem, I'm going to go ahead and start with, we know we're integrating 1,470,000 times 8 minus y dy. The question is, what are our limits of integration? So you're trying to remove half the water. Now, because this is a rectangular tank, if I'm trying to remove half the water, then some are going to think I'm integrating from 0 to 3 or I'm integrating from 3 to 6. I hope it makes sense that we're going to take the water off the top. So we're going to integrate from 3 to 6. So you had a choice, 0 to 3 or 3 to 6, but again, we're going to take the water off the top. So we're going to integrate from 3 to 6. That's going to give us 15,435,000 joules. And if we look at the last problem, then again, I'm still looking at that same interval because it's the same problem. The only difference is how much water we're removing, which the only thing that changes about the problem would be the limits of integration. We're trying to take enough water out so the remaining depth is 2. So again, if I want to leave in a depth of 2, what I have to take out is going to be from 2 to 6, which will give you 23,520,000 joules. Now again, just to kind of close, or at least go back over again the check, if I plug these 2 limits of integration into that depth, then I should be able to get a maximum depth. This is a distance. Plug the limits of integration into the distance here. I should get a maximum and minimum distance. You have to move something. So if we have to move it from here, that's moving 6 units. So you get 6 when you plug 2 into 8 minus y. That's our maximum distance. Our minimum distance is if we were moving it from here. That's going to be a distance of 2. We get 2 when we plug 6 in. Got just about 20 seconds left, so I think key thing to remind you of with your 2 formulas is force is weight density times depth times area, and work is weight density times distance times volume.